Okay, welcome back, everybody. Hope everyone had a good weekend. What I plan to do today is finally finish chapter 7. This is a long chapter. There's a lot of information there. And then probably get through halfway through the next chapter, chapter 8. Okay. In between the chapters, I want to go back to the course website and make you aware, remind you about a particular simulation that will aid you with respect to this chapter and how that can aid you with respect to the bond polarities and so forth. Okay. So anyway, let us continue. Any questions before I continue where we left off? All right. Well, we were on chapter 7, obviously. And we ended up on this particular page. Now, the question here they talked about, let me back up to remember, we were talking about electronegativity and how that is defined. That is the definition of En is the ability of an atom to pull electrons close or pull it onto itself in a bond. Okay, in a bond. And that's going to give us a lot of information with respect to what type of bond, whether it's a polar or non-polar bond. Okay, so here, and then as far as the En or electronegativity, remember that fluorine is our reference point. You know, if we look at the periodic table, we'll see that fluorine is right here. Okay. And that is the most electronegative element that there is. And the trend was from left to right, the electronegativity of the elements increases. And that's why we use fluorine being the most electronegative as our benchmark, our reference point. And if we ever need to determine which direction a polar bond is going to, in other words, if I have a scenario like carbon oxygen here, and I need to determine who is more electronegative, I can find them on the periodic table relative to fluorine. Note that fluorine is right there, in fact, right next to oxygen is right next to fluorine. So compared to carbon, oxygen is a lot more electronegative. So in the bond between carbon and oxygen will pull the electron density toward itself, increasing the electron density around the oxygen, resulting in decreasing the electron density around carbon, which then gives, in both scenarios, a partial negative on the oxygen and a partial positive on the carbon, okay? And we draw the delta notation, which we use the symbol delta, lowercase delta, either as delta positive or delta negative. And then we use the polarity arrow, where the arrow pointed in direction of the partial negative side. And then the arrow had a plus side on the other end, which represents the partial positive side of that particular bond, okay? So we look at the first example and we see that oxygen is a lot more electronegative than carbon. And so we can draw an arrow from the carbon to the oxygen, okay? Which means that the oxygen would have the partial negative and the carbon would have the partial positive, the delta notation. And that is a dipole. In fact, that is a permanent dipole. You know, a dipole, meaning two poles, positive and a negative, okay, which we have here. And this particular bond is a polar bond because we have a dipole, okay? We look at nitrogen and fluoride. We don't even have to look it up in the element periodic table because fluoride is the most electronegative element. So we automatically just draw the arrow from nitrogen to fluoride. And so the fluoride has a partial negative and the nitrogen has the partial positive. Oxygen is drawn in the direction of the hydrogen to oxygen, okay, because oxygen is a lot more electronegative, so that gets the partial negative. Hydrogen gets a partial positive. And we got carbon to chloride. Now, in general, halogens are always going to be the winning partner, if you will, in this bond, if we have a halogen bonded to an atom, because they tend to have the higher electronegativities. And so here carbon has a partial positive and chloride has a partial negative. And then remember what we said about any hydrogen carbon bond, the electronegativity of each atom is very similar. And so essentially they're the same. So we don't, carbon hydrogen does not have a dipole. It is non-polar. So all of these, other than the carbon hydrogen, are polar bonds. And whereas the carbon hydrogen in this example is a non-polar bond. Okay, now we need to know that information with respect to the bonds, because with that information, then we take the structure that we determined from the Lewis dot structures and look at any polar bonds and determine, from that information, determine the overall polarity of that molecule, which then in effect gives us a lot more information once we know what type of compound we're dealing with, polar bond versus non-polar molecule versus non-polar molecule, okay? All right, so let me clear this up and we'll add it up here. So in this case, we got the arrow going from left to right, right to left, right to left, and none with respect to carbon hydrogen, okay? Remember, this aspect here, for some reason, seems to be a little bit challenging. And what I try to attempt to do is use the example, the general example of the bond between A and A, okay? When the species that are bonded together are the same, then that line, those electrons right there, are being shared equally, okay? So A and A are both the same species. So once we recognize that, we can very quickly say that is a non-polar bond. We don't have to go any further, simply because those two atoms are the same. The other example was a carbon-hydrogen bond, okay? Carbon-hydrogen bond, automatically, that is a non-polar bond because the electronegativity is very much similar. And so there's a sharing, an equal sharing of that bond. And the other analogy is the AB. Okay, AB represents two different elements, plain and simple. That's where I sometimes students fail to see here, is that A and B, regardless of what A and B is, the fact that I got A and B, they're different. That in itself automatically tells you I got a polar bond, okay? Automatically. The only exception is the carbon-hydrogen bond, which we just explained why it is non-polar. That means that everything else, anything else that is different, as is the case here, carbon, oxygen, nitrogen, fluoride, oxygen, hydrogen, carbon, chloride, automatically is a polar bond. No questions asked. You don't have to look up anything, okay? So the question could be, is that a polar bond? And you know it is automatically. Now, if they ask you to put in the delta notation and the polarity, well, then that's where you use their relative position of the two, their relative position to fluoride. And whoever's closer to fluoride is the most electronegative, and therefore the arrow part will point to the most electronegative element, resulting this is a polar bond, permanent polar bond, okay? Permanent because it's the nature of the beast, the nature of the bond, two dissimilar atoms that are bonded together. Specifically, non-metal, okay? I repeat that, specifically non-metal, specifically covalent bonds, okay? All right. Clear up my mess. Now, in this scenario, the question is asked, are these bonds ionic? Okay. And then if they ask you, well, which ones are a polar covalent and which ones are covalent? Remember, you got two types of bonds. Let me rehash that for a second here. And it may sound redundant, but it's for a reason, okay? Two types of bonds. And so I have here, okay, I have a compound. Better yet, let me do it this way. I have up in here a compound of some sort. I'll give it to you in generic words. Now, if that compound is made up of a metal and a non-metal, it's ionic. It's an ionic bond or ionic compound. It's ionic. Whoa. Something happened here. All right. Now, the other scenario, if it's made up of a non-metal combined with a non-metal, then it is covalent. Okay, and under covalent, I kind of ran out of space here. I either have a polar bond or a non-polar bond or compound. This scenario is an AA scenario or carbon hydrogen. Okay, the other scenario is an AB scenario, where you have two dissimilar elements. And so that's your flow chart. I got a compound. If it's a metal-non-metal combination, it's ionic. That's it, done. Okay, if it's a non-metal combination, I got a covalent compound. To further classify it and determine if those two nonmetals are the same. If those two nonmetals are the same, or a carbon hydrogen, I got a nonpolar species, nonpolar bond. And if it's not the same, then I got a polar bond. Now, in general, when your molecule is made up of nothing but nonpolar bonds, you have a nonpolar molecule. And if you have polar bonds in your structure and they do not cancel out, and I'll use some examples, we'll go through some examples, and they do not cancel out each other, you end up with a polar bond. If they have polar compound, I should say. If the polar bonds cancel each other out, then you end up with a nonpolar species. Okay. So let's go back. All right. So in this scenario, first thing, is it ionic? Okay. So we look for any metal, non-metal combination. And the only one here, obviously, is the sodium chloride. Now, you might forget, you've got to go back and remember from the periodic table, is it a metal or non-metal? Well, you use the stair step, okay? The stair step on the periodic table. To the left of the stair step, everybody is a metal, excluding hydrogen, okay? To the right of the stair step, everybody is a non-metal. Plain and simple, nothing more, okay? So it's imperative that you recognize who the metal is and who are the non-metal. So you can then identify what type of bond they have. So sodium chloride is ionic, okay? We got BR, bromine, obviously two nonmetals. So that is covalent, no questions there. Phosphorus fluoride, two nonmetals, covalent, okay? Fluorine, fluoride, and bromide, again, covalent. So right now, all we're doing is distinguishing between covalent and ionic. Now we do this for the covalents. We do the further classification. BR. That scenario is an AA scenario. So this is a non-polar bond, okay, and a molecule. Phosphorus and fluoride. That scenario is an AB scenario, which means automatically that's a polar bond. And we already talked about sodium chloride. And then again, we got fluoride and bromide. That scenario is an AB scenario. So that also tells you that it is a polar bond. Okay. And so the polar, you can tell here, we got who are polar. So we got ionic right here, sodium chloride. The phosphorus fluoride is a polar covalent bond. The fluoride and the bromide are a polar covalent bond. And the bromine is a nonpolar covalent bond. Okay. Now, if we needed to draw the dipole arrow, well, with the bromine being nonpolar, no dipole arrow there. It's not polar, so nothing there. Phosphorus and fluoride automatically, since fluoride is the most electronegative, it goes through in the direction of the fluoride. So that gives me a partial negative on the fluoride, partial positive on the phosphorus. Not applicable for the ionic compound. And then we got the bromide and the fluoride. Well, the arrow goes from right to left, because again, the fluoride is the most electronegative. So in that particular bond, we have a dipole, okay, going and is being sent to the direction of the fluoride. Oh, there's a question. Give me 1 second. Okay, so good question. Question is Thomas, and I think that would, I'll explain that one. It's a good question here. I'll explain that because we're going to find that it is possible to have polar bonds in your molecule, but they end up being nonpolar. And that occurs when the polar bonds cancel each other out. And we're going to have some examples of that. And you see that CF4, 4 polar bonds, and you would think, oh my goodness, I got a polar molecule. However, if you do the Lewis dot structure for CF4, you end up with being tetrahedral, okay? And tetrahedral would be, to refresh your memory, one of the most common geometries involved, where you have 2 bonds going in the plane of the screen, and then coming out of the screen, sort of, is another fluoride carbon bond. And then going to the back of the screen, you have another bond, okay? Now, if you were to take that, there's symmetry with respect to this particular tetrahedral. There are 4 polar bonds, but because of the symmetry, okay, I can throw the plane, if I use the plane here, that means the XY between these 2 fluorides, I can cut this molecule right in half. And so this fluoride that goes to the back is a reflection of the fluoride going to the front. And so it's symmetrical. And so in this scenario, all 4 bonds, though they are polar, cancel out. And so we result in having a nonpolar species because all 4 polar bonds cancel out. And I have some more examples of that, how things cancel out. So tetrahedral configuration. And the other one that does the same thing is the trigonal planar, where you have a moiety you could have, I'm going to put in generic terms, where you can have 3 species like this. Okay, where you got 120 degrees all around. Okay, again, that is also symmetrical. There's a plane right here down the center, and the B's are reflections of each other. And so if those A and B 3 bonds were polar, then that species would also be nonpolar because all 3 bonds would cancel each other out with respect to the symmetry. we can demonstrate that mathematically, but then to do that, I got to go through the mathematics and show you about vectors, and we're not going to do that. We're using symmetry to demonstrate that they cancel out. Now, what do I mean by canceling out? Okay, these arrows right here, I may have mentioned this, they're called vectors. A vector is any moiety that has magnitude and direction. And so if I say to you 50 miles east, you got the magnitude 50 miles and you got direction is east, okay? Or it could be southeast or any type, but it is a vector. Now, graphically, we can display vectors with these arrows. And what that means is this, that we can add them or subtract them, okay? So these two arrows, given by their distance, are approximately, they're the same magnitude, same direction. They're all going to the right. And so for argument's sake, we're going to say that the first one is 5 units, second one is 5 units. So cumulatively, since they're going in the same direction, I have a total of 10 units. We use this a lot in physics to demonstrate force. So we like 10 units of force going to the right direction. Okay, 10 units. Now, if I reverse one of these and I have it go the opposite direction, okay, where I got 5 units going to the left, 5 units going to the right. One in the right is going in the positive direction. The one in the left is going in the negative direction because we have our coordinate system, okay? That results in these two going in opposite direction, a net zero. And so if those two arrows, which represent the polarity, if they're going in opposite direction, they cancel each other out. And having a net zero results in a nonpolar species. Classic example would be carbon dioxide. Carbon dioxide has 2 dipoles, one going from left to right, from the center carbon to the right oxygen, and one going in the opposite direction, same magnitude, carbon to oxygen, but they're going in opposite directions, okay? And so the polarity of the right bond cancels out the polarity of the left bond, resulting in the net non-polar bond. So carbon dioxide, though it has polar bonds, just like this one here, because of the geometry, they cancel each other out, resulting in a non-polar species. Okay? If the polar bonds don't cancel out, then we have a polar molecule. If if the molecule has all non-polar bonds, you end up with a non-polar moiety. Okay, good question. We'll have some more here again. So polarity, I mean, it shows up. Polarity is a very important concept in chemistry. As organic chemists, ones that synthesize compounds, make new compounds, even chemistry, even the chemistry in our body. If it wasn't for polarity, chemistry wouldn't work. Chemical reactions wouldn't occur spontaneously as they should be working because of the polarity. We got a positive and a negative. We got a dipole, which then we can use another dipole to interact with that dipole to create new compounds. So it keeps showing up. And like I said, consider it like a tug of war in bonded electrons. It's either an equal tug of war, equally shared, or an uneven tug of war, okay? An uneven. Now, in the case of ionic compounds, we had a full-fledged negative charge or positive charge. With respect to covalent compounds, we do have a charge, but it's a partial. It's just a partial charge, okay? All right. Here we're asked the question, okay, get a list of compounds. Everybody, they want to know who's ionic, who's polar, and who's non-polar. Okay, so we can very quickly determine all the ionic bonds. It's a metal-non-metal combination, so you know what? We got sodium chloride. We go down the list. The only other one is the calcium and oxygen. Those two are the only ionic compounds that we have here in the list here, okay? So it's ionic because we have a metal-non-metal combination. The HCl we have, so HCl, we have the scenario where we have the AB scenario. Two dissimilar atoms, automatically polar bond, okay? And covalent, all right? Polar covalent bond. Here, HH, hydrogen, that scenario is an AA bond. Both the species are the same. It's a covalent bond, but specifically it is a non-polar covalent bond, okay? And then we got the chloride and the carbon, which again, in this scenario is an AB scenario, okay? And so that example is a covalent bond, but polar, okay? Polar. And then the carbon hydrogen, no questions asked, it is very similar, treated as an AA scenario, okay? Because all the electronegativity of both atoms are very, very close. So we treat that as a nonpolar covalent bond. And if you think about it, a lot of oils, vegetable oils and so forth, a lot of them have a lot of carbon hydrogen bonds, very nonpolar. They don't mix very well with species that have polar bonds like water. Oil and water don't mix. And that's attributed to the polarity of the species. Then we have oxygen, which again is an AA scenario, which tells us that we have a nonpolar covalent bond. Potassium, oxygen, no questions asked, that's ionic, okay? And then finally, we have a dissimilar situation where we got an AB atom-wise, and so automatically a polar species, specifically a polar covalent species. Now, you might need to draw the arrows, you can, because in this scenario, we got the first one, the HCl. Obviously, we're not gonna, no arrows for the ionic compounds and carbon hydrogen bond, ionic compound. So we're gonna have arrows for the rest. So hydrogen chloride, the arrow should be going from left to right, okay? Because chloride's a lot more electronegative. So we get a partial negative on the chloride, partial positive on the hydrogen. Carbon chloride going from right to left. Ooh. Right there. You got a partial positive on the carbon, partial negative on the chloride. And then here we have no, what did I do here? No arrow on the oxygen, okay? And then phosphorus and fluoride automatically toward phosphorus. And partial negative on the fluoride, partial positive on the phosphorus. Okay, so we're going to talk about how I just mentioned about how polar bonds can cancel, and if they cancel, then we end up with a nonpolar species. Now, when you look through the molecule and they have all nonpolar bonds, which includes the carbon hydrogen bond, okay? All carbon hydrogen bonds or all the elements are the same, like diatomic and so forth, you end up with a nonpolar molecule, okay? When the polar bonds do not cancel out, then you end up with a polar molecule. Okay, looking at these two examples. We talked about carbon dioxide, okay, down here at the bottom. You see where the arrows, one goes to the right in the positive direction, one goes to the left. So we have our net here, polarity is equal to 0. Okay, we end up with a nonpolar molecule. With respect to, and this is carbon dioxide, and this is sulfur dioxide. And you would think, well, maybe sulfur dioxide is the same. Well, the difference is this: sulfur brings in an extra pair of electrons, okay? So we end up with a lone pair up here. And we would think that this would be similar to that, the triangular example I used earlier where I had A and then 3 B's sitting out here. And you might say, oh, wait, it's symmetrical. You know, why don't they cancel out? Well, the difference between these two here is this: we got a lone pair on the central atom. What happens is that lone pair causes that bond angle to shrink. And so now it's no longer symmetrical. It is bent, okay? For sulfur dioxide. This is symmetrical in this scenario. This is not. The result is that the dipole, this one's going in, say, in the southeast direction. This is going in the southwest direction. They don't cancel out, okay? So the net is polar species because the polar bonds do not cancel out as they do with carbon dioxide, where they do cancel out, okay? And so if polar bonds cancel out, you end up with a nonpolar molecule. If polar bonds do not cancel out, you end up with a polar molecule. And that scenario here, like the AB3 here, the symmetrical, or the tetrahedral where you have all the same species, you know, with, I can use chloride, for example, or fluoride. If they're all the same, you got 4 polar bonds, okay, then you end up in a nonpolar species, okay, in the tetrahedral configuration, because the geometry of them cancels there. Now, the moment, here's you got to keep this in mind. The moment I replace one of those bonds with, say, something else, call it bromide. So now I got 3 chloride carbon bonds and 1 carbon bromide bond. Now, the magnitude of those 3 bonds is no longer the same. 3 of them are the same, 1 is not. You will get a net polar molecule because the magnitude of each bond is different, okay? Is different. And even though it's symmetrical, they will not cancel out. So you end up with a polar species. All right. So some of the things we can talk about here is the carbon hydrogen bonds, all nonpolar species, regardless of if it's a hydrocarbon. Remember, I mentioned to you the general name for a hydrocarbon. It is a chemical that made up of nothing but carbon and hydrogen. When it's a hydrocarbon, regardless of how many carbons or how many hydrogens, it is a nonpolar species, okay? So it has all nonpolar bonds. It's going to be a nonpolar molecule in this example. Trichlorophosphorus trichloride is polar, because if we do the Lewis dot structure for this, you will see that you end up with a lone pair on the central atom, okay, for this species. And I can tell you in general terms that whenever you end up with a lone pair on the central atom, you always don't have to go any further and determine that this species is polar, because that lone pair will create the decrease that bonding, okay? And then carbon dioxide, we just talked about how the polar bonds do cancel out, and we end up with a non-polar species. So the takeaway here is this, is crucial, is that if you have, it is feasible, it is possible to have a molecule with polar bonds and be classified as non-polar, okay? If those polar bonds cancel out. Now, what can we take away from this? Well, right away, if I needed to determine the solubility of carbon dioxide and trichlorophosphorus trichloride, because PCl3 is polar, that would be a lot more soluble in water than CO2, okay? A lot more soluble in water than CO2. Now, CO2 doesn't really dissolve in water. It kind of hangs in there, kind of, because you know you can take a soda pop and shake it. What happens to the CO2? It shoots right out. It's just hanging in there, being held by the water molecules. It's not truly dissolved, because if you were to really shake it and it dissolve, it would not be bubbling up on you. Okay. All right. So you might want to do the ammonia. We did talk about the water. We talked about ammonia, and we talked all those cases. They're both, you know, the ammonia. We ended up with, remember, to refresh your memory, 3 hydrogens with a lone pair. Water had 2 lone pairs. Water is extremely polar, okay, because it's got 2 lone pairs on the central atom, really decreasing the bond angle, really, very polar. Most polar liquid there is that we're aware of, water. And ammonia, just like the PCl3 scenario, okay, with the lone pair, polar species, okay, that lone pair plays a big role there. Okay, well, that, ladies and gentlemen, brings us down to the end of chapter 7. What I want to do is take you to, here we go. Give me one second. Okay. All right. If you go to the course website, one of the modules that has some additional resources is labeled additional chemistry resources. I believe it's the second module. And in there are some simulations. We worked with the first one, we were balancing equations, another good simulation that we're going to eventually work with that you may want to take a look at. But the one I have an interest in right now is called the molecule polarity. If you click that, it gives you this link, and from there sends you to the website of simulations. And you got 3 choices here, but I would select right now the 2-atom choice. Okay. The question, Thomas, is, so is the shape in tetrahedral, is it always nonpolar? Again, it depends on what's bonded to those 4 atoms. If it's all nonpolar bonds in a tetrahedral like methane, yes, it is nonpolar. But if one bond is polar bond and the other 3 are nonpolar, then overall it's a polar molecule. And in fact, you can go around. Let me demonstrate that. Come back to that in a second. So the tetrahedral is in the shape. You know, go back to your shapes table and you'll see that. But let's do methane. Okay. All right. So in this scenario, tetrahedral, I'm trying to draw it in a kind of 3-dimensional fashion. Again, the solid lines are in the plane of the screen, the wedge coming out of the screen, and then the hatch mark is going to the back of the screen to kind of give you a 3-dimensional perspective. Now, methane here, CH4, all carbon hydrogen bonds, okay? All nonpolar bonds. So overall, we have a nonpolar species, okay? Now, if you put in, let's say, an halogen, so we now replace one of those hydrogens with, for argument's sake, we just say coal, okay? Okay. And so we have 3 nonpolar bonds and 1 polar bond. Okay, the carbon hydrogens are nonpolar, but we have 1 carbon chloride, which is polar. The result is that this species right here, well, 1 chloride, is polar. Okay, and if we continue and say replace another one, Okay, if we go around the horn, we can continue this one here. Now we have two nonpolar and two polar bonds. Everybody agree on that? All right. So the result is overall, it is still polar. Continue to replace the third one. So we end up with this one. So even though it's symmetrical, the fact is that these three bonds do not cancel each other out. So we end up with a polar species. Until such time that we go back to where we started and we got all four with chlorides. Okay, now we go back to a nonpolar because in this case, the four polar bonds do cancel out. So this geometry of a tetrahedral can end up in becoming nonpolar if you got polar bonds, but it depends on how many of each one you have. And so you can go around the horn to eventually you start off with nonpolar, polar, 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 and then come back to a nonpolar. Okay. So symmetry we don't touch a lot on. I'm just giving you the very basic parts of it. So whenever you have symmetry that can show you that bonds cancel out, you end up with polar bonds, non-polar molecules if the polar bonds cancel out. Okay.
Thank you so much.
All right, no problem. So we were going to the simulation, and here I wish they would have labeled this A and A right now, but we'll just go with the A-B scenario. So, but we have green here. When it becomes red in color, that is the increase of electron density. So when an atom, you see this bond here between A and B. Right now, the electronegativity in this example is essentially the same. So this could be an example of, say, carbon and hydrogen, right? Even though they're different, their electronegativity is essentially the same. And if I were to do electron density, which probably maybe a little bit better here, that gray area you can see is symmetrical. That gray area represents the electron density around the A and the B, okay? The blue, it's the same thing, the blue, I'm trying to, by no color here, you can say it's symmetrical. Now, the moment I start to increase the electron density of one of them, and let's just say we're going to change B to something else, okay? Notice we start to get red color, and not only that, we create the dipole arrow. Okay, because here the red color represents the electron density. B's electronegativity is increased much more than A. So it's starting to pull the electron density onto itself, resulting in that particular dipole arrow, where the arrow is going toward B because the electronegativity of B is greater. And A starts to pick up, it starts to lose electron density. There's a decrease of electron density, so it's getting a net positive character. So we call that a partial positive. Okay, it doesn't mean it's not negative. There's electrons in there, but not as much as it was before when they're equally distributed. So we start creating a dipole, okay? And that's what's happening here. If I increase the arrow, you can see how blue it gets. In fact, let me clear this up. If the character is, if the difference is quite large between the electronegativity in this example, we literally have an ionic compound. So this could be an example of let's say sodium. Oh, and this could be an example of, let's say, sodium ion and the chloride ion. See, notice here, there's no sharing of electrons. It's just a totally attraction of positive and negative, okay? because the electronegativity between the two is so large that literally there's no sharing going on, that one atom is gonna take the electron density completely, okay, than the other. So we end up with a species with a lot of ionic character. And so a more covalent character would be something like this, okay? And it puts a charge in. Now, what can happen is if I put an electric field in it, sure enough, the molecules will line up, okay? With the plate, the negative, partial negative will be attracted to the positive plate in the electric field, okay? One way to line up the molecules, okay? And if you don't see the red color, well, maybe change it over to the electron density, and that gray scale just shows you the darker it gets, the more electron density is going on to the B side. You know, and it could be the opposite side, not necessarily B, it can go this way too. All right, it all depends on the atoms A and B, whatever they may be. So that kind of shows a little bit more about polarity, and a very, very important concept in chemistry. Very important. All right. Any questions? All right. Well, you know, with that, use that simulation app to give you some more insight into the bond characters, ionic versus covalent. All right, so it brings us to chapter 8. Chapter 8 deals with nomenclature. Now, throughout the time here, I've been introducing the nomenclature, which is nothing more than name that compound. Now, you have a link on your course called StudyMate. That will help you. I've uploaded, I forget how many examples of compounds. That'll help you with helping you to learn how to name these compounds, okay? And this naming is called nomenclature. What is the name of a particular compound? Because we want to get to the point where you're given a name, you can write the formula, and the other way too, you're given the formula, give us the name, okay? All right, so for simple neutral atoms, you know, we add the term, like for example, sodium atom, that we're talking about the element, or we're talking about neon element. Now, we mentioned this before, be familiar with the first 20 elements. And then I think we added a few more here. Ba is barium, Co is cobalt. We got iodine. Okay. We've got barium, cobalt, iodine, copper, iron, lead, mercury, silver, and gold. These two get mixed up quite a bit because of the A. But gold is Au, silver is Ag. Then we've got zinc and Sn. You can either call that stannous, if it's an S, you may see it named as stannous, or tin. You're better off just to use the term tin, Tin, just like it's a metal. And in fact, next time you are brushing your teeth in the morning, take a look at the box of your toothpaste or the ingredients. You might find stannous fluoride. And so you're brushing your teeth with tin, Tin, fluoride. Then strontium, nickel, bromide, chrome, manganese, and cadmium. There's some other ones there, okay? We'll be adding more as we progress. We're not gonna add all 118, but we're gonna have quite a bit, okay? As by definition, an ionic compound, you should know real well by now, is a combination of a metal and a non-metal. Okay, whereas covalent compounds is a combination of nonmetals only. Also, you see the term molecular compounds. Okay, we have a lot of monoatomic ions: sodium chloride, calcium ions, and they have their respective terms. Now, on the periodic table, at least the one I have circled 16 elements that have an known charge 100% of the time, okay? Somebody asked me this in my earlier class, how do we know that magnesium has a +2 charge? How do we know that magnesium has a +2 charge? Let me ask you guys. Magnesium, how do I know that? How do I know what kind of ion magnesium will form? Okay, well, let me give you a hint. Where's it at? Here's magnesium right there. Okay. What type of ion will magnesium element create? What charge would that ion have? A positive charge, Samantha, would be correct. Okay, that's half correct. Let's get the other half. Specifically, what is the magnitude of the positive charge? You are correct. It is a positive charge. In fact, everybody, +2, you got it. Exactly. Okay. Specifically, everybody here would have a +2 charge. Everybody. Okay. As an ion. And everybody that I circled in red in the first column will have a +1 charge. Everybody. Okay, that's 12 elements that you know 100% of the time what their charge would be as ions. Calcium will have a +2, magnesium will have a +2, beryllium will have a +2, strontium will always have a +2, etc., etc. Lithium will always have a +1, sodium +1, potassium +1, etc., etc. Okay, because what they all have in common is this: one, they're all metals. Two, all metals lose electrons. Put that in long-term memory. And the number of electrons they lose depends on what group they're in. If they're in group 1, they all have 1 valence electron. They're going to lose 1 electron, the outermost shell, the valence electron. Okay, because they're not going to pick up 7 electrons to get that happy 8. There's too much energy involved. Much easier to get rid of 7. Get rid of 1 than try to add 7 in there. Okay, so 100% of the time, you know what their charge would be. Then additionally, there's 4 more, and I circled those. Okay, you have aluminum right here, you have zinc right here, silver right here, and cadmium right here. Respectively, aluminum will always have a +3 charge, simply because it has 3 valence electrons. Now, everyone else in here, we cannot predict all the metals. We cannot predict what kind of charge they're going to have. It varies, with the exception of these 4. Zinc will always have a +2, 100% of the time. Silver always has a +1. Cadmium always has a +2. So therefore, there are 16 metals that you know will know 100% of the time what their charge will be when they become ions. Okay. And if you're asked, oh wait, what's the charge of magnesium? +2. Calcium, +2. Potassium, always +1 of the ion. Okay. Aluminum, always a +3. Okay. So there's 16. And I think I told you this, I call these the sweet 16. That's important. Why? Because when we get to name compounds, if the compound does not belong to the sweet 16, then to identify what metal we are using, we have to use Roman numerals. And why is that? For example, copper can exist as either a +2 or a +1. It's very ambiguous. We don't really know, depends on the conditions, okay? But to distinguish between the +2 and the +1, we have to use Roman numerals to say copper Roman numeral 1 or 2. So we'll write copper, parentheses, Roman numeral 1. That designates that as copper +1, okay? If we say copper, write copper, Roman numeral, well, in parentheses, Roman numeral 3 and parentheses. Oh, not 3, 2. Sorry about that. Let me erase that. I got carried away else. This is 1, and then Roman numeral 2. That is copper +2. Okay. And that's important because we could be given the name copper, parentheses, Roman numeral 1, and parentheses, and that tells you you're working with copper 1. Okay. Or you have to name it. That's how you name it. You have to be specific. Everybody else, the Sweet 16, no Roman numerals. Okay, because those metals have a known oxidation number all the time, 100%. And it's been shown, there's an organization worldwide, the IUPAC group, that their job is to basically agree on how to name compounds. What's the correct name? What's the official name? And that is so all of us, all the chemists, scientists in the world, regardless of what country they're in, that we're all in the same boat. Because in the old days, they used to use, for example, copper 1, copper 2. They used to call it cupric and cupris. Very ambiguous, very difficult sometimes, and confusing to keep them straight as to which one you're talking about. Now, with this nomenclature method with Roman numerals, no questions. You know exactly which metal you are talking about. Okay. All right. All right. Now, the polyatomic ions, where are they? Well, I direct you to the periodic table. Down in the bottom left corner, we have here labeled most common polyatomic ions. That by far is not a full list. There's a lot more, but those are the most common ones that we're going to use here in Chem 130. And each one has their own specific name. First of all, they are ions. And being ions, you're either going to have a negative or positive, okay? Second of all, they are covalent compounds, but because they have a charge, they're ions, though they are covalent. And thirdly, they each had their own specific name. So this polyatomic ion, for example, has a nitrogen bonded to 3 oxygens, and it has overall -3 charge. Its specific name is nitrate, okay? Nitrate. It's not nitrogen trioxide or anything like that. It's called nitrate, okay? And this is true for all the other ones. Now, if for some reason we need to demonstrate and show more than one of these nitrates, what we do is we write a parentheses around it, and then we do a subscript. For example, if we need to show 2 nitrates, so we would put parentheses in the formula, and then maybe put a 2 in the subscript, okay? We will use parentheses to keep the nitrate, this is the nitrate ion, intact. We wouldn't do this, and I've seen this before, because you need 2 nitrates. I've seen where people have written N2O6. That, I have no idea what that is, but it's not 2 nitrates, okay? not 2 nitrates. So it is parentheses, subscript with whatever number nitrates you need. All right, let's go back to that. So I've been using the term charge, and that's be okay when we're dealing with ionic compounds, because we have a positive or positive 1, 2, or 3 ionic charge or negative ionic charge for these ionic compounds. But covalent compounds don't have a full charge. They have a partial positive, negative. Okay. Well, but their oxidation state is the same. So it's just a fancy name for the charge. Be it if it's an oxidation state as an ionic compound or as a covalent compound, I'm going to use, that's the term I'm going to start using. Okay, I've been using the term, the charge, and I'm going to try to slowly convert to what is the oxidation state. What is the oxidation state of the sodium ion? There will be a +1. Okay. All right. Now, all elements, as we stated earlier, I stated before, have a net carbon to 0, the elements, okay, because they have equal positive protons and an equal number of negative electrons. So it gives you a net 0 for the elements. Now, it is only when they lose or gain electrons that we end up with the ions, okay? And they talking here about fixed charges. I already showed you the 16 to have a fixed charge, and all the other metals would have a variable charge. Okay, and it can vary. For example, copper, in this example, could be copper plus, copper 1, or copper 2. They even have different colors. One's a blue color, one's a greenish tinge color. Totally different properties. Okay. We should know this by heart now. Metals lose electrons. They want to become ions. We talked at length about their respective charges. This is only true for the A elements, okay? For the A elements. And that is column 1A always has +1. 2A always +2. 3A always +3. Then we added the zinc and the cadmium, okay? And then the silver, okay? And then that means that all other metals can vary from +1 to a +9. It all depends on their reaction conditions and what's happening, but we can't predict what they are. We can calculate what they are, okay? And you might say, well, how do we do that? Well, let me tell you. Okay, if you are given, well, no, let me not tell you just yet. I got to give you some more information. Okay, so that means that for the ones that do not have the sweet 16, that have an exact oxidation state, everybody else can vary from a +1 to a +9. So we have to use Roman numerals. Okay, and some examples here. Here we have lead 4. When we write its name out, it is lead Roman numeral 1B. Don't forget the parentheses around the Roman numerals. Here's copper 2. Here's iron 3. There's basically, like I say, copper. There's copper 0, the element. There's copper +1, an element that's lost 1 electron, and there's copper +2. Okay, 3 different properties of the same element. Iron the same way. We've got elemental iron. But iron could have a +2, and there's examples of iron with a +3, okay? 3 types. Lead, too, can have a variety of oxidation numbers. Depends on how they're bonded, okay, and what's happening there. Okay, we know about the anions. We know that group 3, which brings me to a point. I read a few places in some of the answers for some of the questions in the exam that comments like metals can lose or gain electrons. Okay, that's not a, for Chem 130, that's not a true statement. Metals will always lose electrons. And the same is true for nonmetals in that they will always gain electrons. The number that you gain depends or lose depends on what group they're in. So group 5 are nonmetals, okay? Because group 5 nonmetals want to gain electrons. They already have 5 valence electrons. They're only 3 away from having that magical 8 number around them, okay? That's the driving force to get to the 8. Therefore, they would prefer to gain 3 electrons rather than lose 5 electrons, okay? By gaining 3 electrons, now they got the octet fulfilled, plus now they are ions. And that's why those elements in group 5 are a lot more stable, because now their octet has been fulfilled, okay? Group 6, they're only 2 electrons away. So they're going to pick up 2 electrons, resulting in a negative carbon. Okay, group 7, they're right next to the noble gases that they're, quote, happy, right? Because their octet has been fulfilled. And group 7, they're only 1 away. So everybody, every nonmetal in group 7 will gain 1 electron, resulting in an overall -1 charge, okay? -1 charge. Now the fluoride, being always having, being the most electronegative element, will always at all times have a -1 charge. The other ones, you'll see that they can vary, but in general, all the halogens in group 7 will always gain 1 electron. And obviously we know about the noble gases, they're not going to gain anything. They're already at the 8 mark. Okay. Ionic compounds, the metal-nonmetal combinations. We're going to begin by learning formulas and names for ionic compounds. So remember that when we're dealing with ionic compounds, they are ions. So you might be given the element and asked to write compound from these elements. So the first thing you got to do is to convert the elements into their respective ion. And you do that by knowing their position on the periodic table and whether it's a metal or non-metal, as if they're going to have a plus or a negative, okay? Now, the thing about this, when we put them together, is the number of cations that we utilize and the number of anions that we utilize must equal to 0. Okay, so if I have a +1 ion, then I must need one -1 ion to put them together. Sodium chloride. Okay, sodium has a +1. The chloride has a negative, so 1 to 1. Okay, when I write the formula, I simply write them together. NaCl. That is this formula for sodium chloride. Okay, and their sum equals 0, 1 of each. Now, if, for example, I have magnesium. Let's do magnesium, right? Well, if you don't know, you should know that magnesium always has a +2. It's a group 2 element. It's a group 2 metal. It will have a +2 when it becomes ion, okay? Well, with the +2, I'm going to need 2 chlorides to counterbalance the +2 for magnesium, okay? So I write 2 there in front of the chloride, just to remind me that I need 2 of them. And so when I write the formula, that 2 would become the subscript. So it would be MgCl2. And that would be the formula for magnesium chloride. Okay. All right. I talked about the polyatomic ions, but we'll be using some of these to create some compounds, okay? And again, think of them as a group, as a single entity with their own specific name. We don't change the name, okay? And if we need more than one, we're going to put a parentheses around it. Okay, if we only need one, no parentheses needed. As we put them together, they're going to end up to 0. So the number of cations plus the number of anions must equal to 0. So you might be given the question says combine sodium and nitrogen, right? So here's the nitrogen. Well, what we need to do is convert those elements first into metal. We know that sodium is in group 1. So sodium is an ion, will be A+1 charge, okay? We look for nitrogen. Nitrogen's in group 5. Nitrogen in group 5 would need 3 electrons. It's a nonmetal to give us a -3 charge. Okay. Plus, what's important, the name went from nitrogen as an element, and as a ion, we changed the name to nitride. Okay, when it comes to naming these compounds, it's always the anion that gets its name changed. The sodium, the metal, remains whatever name it is. Sodium, be it an atom, be it an ion, is still sodium. It is the anion that gets changed. So keep that in mind because we're going to name it afterwards. So now we have 1 positive and -3. So that tells me that I need 3 sodiums to counter the -3 charge for the nitrogen. So that 3 becomes a subscript in sodium. So now the formula for sodium nitride is Na subscript 3N, okay? Nitrogen became nitride. Sulfur will become sulfide. Oxygen will become oxide. Okay. All of the halogens, start fluorine down, become the halides. So chlorine becomes chloride, fluorine becomes fluoride, etc., etc. What else am I missing? Nitrogen is nitride, phosphorus becomes phosphide, and so on and so forth. Okay. All right, so there's the formula, Na, N. Now, it works both directions. Okay, let's say you're given the formula for this, okay? And you're like, I don't remember for whatever reason what the oxidation number is for nitride. But you do know that it's got to be negative, right? What else do you know? You know, sodium will always be a +1. And there's 3 of them. And so what we have here is a +3 plus the nitrogen equals to 0. We have a little algebraic equation, right? Nitrogen. Right, so we can solve for nitrogen. So rearrange this, so it becomes nitrogen equals to a -3. So that means that this nitrogen with 3 sodiums has to be a -3. Okay, so we can use that to our advantage. And this is how we are able to calculate the charges that we don't know of. For example, let's say you're given copper chloride. Okay, that's all you know. Copper chloride. But this is not one of the exact ones. Elements, it's copper. So we need to figure out which copper this is. Well, we set up an algebraic equation, a simple one. We know that every chloride is in group 7. There's 2 of them. So total, we have a -2, right? So we have copper plus a -2 equals 0. And if you solve for copper, copper equals a +2. So in this state, copper must be a +2, which means that that parentheses gets replaced with Roman numeral 2. So that name will be copper Roman numeral 2 chloride. You will always know the oxidation number of either the anion or the cation, okay? And that allows you to calculate for these that have a variable oxidation state, which oxidation state they're in. Most of the time you're dealing with knowing the anion and you're calculating what the cation is. All right. Oh, you know what? We're running out of time here. All right. Tell you what. Let me stop it here. What's the time? I stopped it in the same spot my 1 o'clock did. All right, let's stop it here and we'll continue